the stage. Yes.
Okay, thank you very much. Let me first check that you can hear me well there in the common room. And let me see if I share my presentation and if you can see that.
Yeah, we are seeing fine.
Room, okay. Okay, yep. Well, hello everybody. Thank you for the opportunity to give this coffee talk to all of you. My name is Enrico Rinaldi. I am a visiting scientist in iTHEMS and at RQC, and I work for Quantinuum K.K. here in Tokyo. And today I want to give a very basic talk in the spirit of the coffee meetings. And I hope, even if you're not an expert, you actually get something out of this talk. If you are online or in the room, please, when you have any questions, just speak up and interrupt me at any time. There's no need to raise hand or anything. Just tell me that you have a question, okay? All right. So today you will learn how to use quantum computers without quantum computers. And in fact, everything I'm going to show you is classical. I want to give a short introduction about simulating quantum computers using classical machines. So there is a lot of research in this specific topic, many years of literature and grant money spent on this, but I want to focus on a single example of simulating quantum computers, which goes under the name of state vector simulations in the Schrödinger picture. What this means is basically this equation here on the slide, and I'm using the bracket notation to denote quantum states. Let's see if I have a pointer. Maybe not.
We are seeing us.
You see the mouse?
Yeah, very small. Yeah.
So this one is a cat, and it represents a quantum state. And so a simulation of this operation starts from defining the quantum state, then acting on the quantum state with an operator, and the result is a new quantum state. Now, it's called state vector simulation because these are vectors in some vector space, and they represent a state. So let's see, how do we represent these quantum states on a computer? Well, the basic thing to do is to start from the fundamental unit of quantum states, which is 1 qubit. A qubit has a state vector psi represented as the superposition of two basis states, 0 and 1, with some coefficients in front, A0 and A1. So to represent the state of 1 qubit, you need two complex numbers, and you need an orthonormal basis in this two-dimensional vector space. If you have, in general, n qubits, the quantum state of n qubits is just the extension of this, where now you have many more basis states and many more amplitudes, complex numbers. How many more? Well, we know that for n qubits, we need 2 to the n complex numbers or amplitudes, these coefficients here, to represent the state. So for 1 qubit, you just have these two numbers, A0 and A1, and that's all you need to represent the quantum state. For 2 qubits, you need 2 to the 2, 4 amplitudes, and these are the numbers here. And this goes on all the way to n qubits. All right. So if you think that one single complex number, if you want to store it in a computer, it requires 16 bytes of memory in double precision. Then naively, to store the information about the quantum state of n qubits, so in order to store 2 to the n complex numbers, you need 2 to the n plus 4 bytes. So basically, a laptop with 32 gigabytes of memory can store at most a state vector of 31 qubits. And that will basically burn your laptop because you cannot even run your OS if you're storing just a single state in the entire memory of your computer. And one extra thing to keep in mind here is that if you add 1 qubit, you're actually multiplying by 2 the number of amplitudes. So you're doubling the memory that you need to store the state of n plus 1 qubits. So this seems very hard, especially if you care about representing the state of more than 31 qubits. But this is just about the state, and I haven't talked about doing any simulation right now. So the thing that typically we want to simulate are circuits, and circuits are sequences of gates or operations. So a circuit C, which is here in front of this state psi0, is a sequence of operations acting on the qubits of the state. So remember, if we have a 1 qubit state, we can represent it with these 2 numbers and 2 basis vectors. So it will look like a 2-dimensional column vector with these 2 complex numbers inside. Now, a gate or an operation that acts on this 1 qubit state is going to be represented by a matrix, a 2-by-2 matrix. And there are different types of gates that do different things. And we also know that there are specific sets of gates that represent a universal computation set. And here I'm just showing some examples. For a 2 qubit gate, you now need to act on a 2 to the 2, a 4-dimensional vector space. So your 2 qubit gate will be a matrix that is 4 by 4. And these are another pair of examples. So if you want to act on a gate on 1 qubit and you have 2 qubits, when you act on the first qubit, you only act with the matrix on the first 2 amplitudes. And when you act on the second qubit, you act on the second 2 amplitudes. And this can be extended to n qubits and also to multi-qubit gates. So the punchline here is to do a state vector simulation of a quantum circuit, you just need to do matrix multiplications. Okay, so that's all there is to know about quantum computers. And this is what high performance computing is good for. Just perform a lot of matrix vector multiplications. And there have been a lot of examples of large HPC clusters where people run this type of simulations. Here on the right, I'm showing some of the fastest supercomputers in the world up to maybe a few years ago, and the amount of memory that they have on their nodes, and the theoretical maximum number of qubits that you can store on these systems. So even on the largest supercomputer in the world, you will only be able to simulate 47 qubits, theoretically, at least store the amplitudes of those 47 qubits. Here is another example down here, where the K computer, the predecessors of Fugaku, was used, and people were able to actually simulate this amount of qubits. The same was done in Jülich in Germany on Juquin, in China on Sunway, And these are another pair of cluster computers, again, in Jülich in Germany. So you can see that at most, people have to be below 50 qubits in order to simulate these state vectors on classical machines. And I only mentioned these state vector simulations, but of course, there are other kind of simulations that allow people to simulate more number of qubits and specific quantum circuits where the gates have a specific structure. But I don't want to get into those details. So one thing I want to mention that I really like is the ability to use GPUs to run a simulation of a quantum circuit. And NVIDIA has a open source SDK that can be used to simulate quantum circuits on many GPUs at the same time. So if you have a large supercomputer where each node has a bunch of NVIDIA GPUs, you can scale your quantum computing simulation to the entire machine using this specific code by NVIDIA. The state vector simulation is limited by memory, as we saw. So it can only go up to 48 or 50 qubits. But it can run, in theory, any depth of the circuit, which means any length of a sequence of gates. So here you can have a sequence of gates acting on 1 qubit that goes all the way to 100,000. And in particular, algorithms that are going to bring us some sort of quantum advantage might have to be very deep and have many gates. So a state vector simulation can be done, but only up to the limits of the memory, which is around 50 right now, or 48. A different type of simulation method based on tensor networks that we have heard at other coffee meetings in the past can let you simulate more qubits, but it is restricted by the depth of the circuit. So you cannot run any circuit. You can only simulate specific circuits with a certain depth. Okay. So the next thing I want to say is that we probably wouldn't need to simulate quantum circuits if we have good quantum computers. So in this slide, and I have references about all this in the final slides that I can share with you if you want. You see many different quantum hardware platforms on a plot that has the number of qubits on the y-axis and the error rate of a 2-qubit gate on the x-axis. And having a, well, I don't think this is, yeah, I think this is the fidelity. So it's like 1 minus the error. No, this is the error, sorry. Yeah, so 100% error is bad and 0.01% error is good. So you want to have the smallest amount of errors per number of 2-qubit gates. If you make an error every time you apply a 2-qubit gate, you're not going to go very far. So you want your error rate to be pretty small. And on this table, again, we see that in the yellow region, below 40 qubits, you can simulate classically with a state vector simulation any amount of quantum circuits, and you can do it on a server with a few terabytes of memory. If you go above this, then you would need a quantum computer or some specific methods. But if the quantum computer is too noisy, you will not get accurate results. So it's not going to be useful for applications. So the good region that you want to try and enter with your quantum hardware is this green region up here at the top, where you have good computers with small error rate, but you also have big computers that cannot be simulated classically. Okay, so I think I'm good with time. Let me just mention one of the recent hardware upgrades from Quantinuum, which is the system model H2, which has 32 qubits. So you can see that at 32 qubits, this is something you can do on a laptop with 64 gigabytes. At least you can store the entire state vector of the H2 quantum computer on a big laptop. And as more qubits get added to the system, the simulations become harder and harder because the memory requirements grow until you reach the size of a supercomputer, and it becomes impractical to do classical simulations, and it becomes important to control and verify the quantum simulations on the actual quantum computer. This is all for my talk, and I am sharing a list of references where I took the plots that you saw in my talk, and some of the tables from the slides. Thank you very much.
Yeah, thank you very much, Enrico, for very stimulating talk and a report from the cutting edge front of this research. So any questions from the common room, perhaps? Just speak up. Go ahead.
So you show that the tensor network, there is a limitation of this gate operation. Why is it so?
Yeah, because to simulate tensor networks, to compute, for example, expectation values from tensor networks, like this one here, you need to find a contraction path. And if the circuit is deep, the algorithms that find this contraction path scale exponentially bad with the length of the contraction. And actually, the physical intuition for why some circuits cannot be simulated with tensor networks is that in tensor networks, you cannot really store a large amount of entanglement. So if your circuit has many entangling gates and creates a lot of entanglement, then any approximate tensor network method will fail at reproducing the correct result, because the approximation that is made with the bond dimension, for example, is not good enough.
So is there any way to make a hybrid of the state vector simulation and tensor network in some way? Are they exclusive, or they can?
There is no need to use a tensor network if you can run a state vector.
Yeah.
And there is no need to run a state vector if you can run a tensor network. But yeah, I don't know of any combination.
But if you go to the white region, then tensor network doesn't work. So is there
Tensor network doesn't work here. No.
Right. Yeah.
I mean, I talked to NVIDIA the other day, and depth of 100 at 50 qubits, actually for them, it's almost impossible to run. So this blue region is actually a bit optimistic here.
Okay. Any other questions?
Is double precision enough? Because if the circuit depth is as deep as 100,000, then the floating point errors may grow. So is there a way to suppress those kind of classical floating point errors?
Yeah, this is all classical, so you can use all the standard classical techniques to do to correct for errors and floating point errors. And there are also compression algorithms to reduce the amount of floating point errors. So you can, for example, run lower precision and still get good accuracy, so that you don't need too much memory.
Actually, I'm able to run those kind of very deep circuits in the simulation.
Yeah. So your question is if you can do it? Yeah, you can do it. Yeah.
Any other questions?
Forward other microphone.
Can you hear me?
Yeah.
So I just wondering, do you have any comment about a few years ago, John Martinez in Google, they say they mentioned they reached to quantum supremacists. So basically they just do something classical computer cannot do. But based on your plot, the Google error bar is quite high. So what's your comment here?
So I think so the fact that they have more than 40 qubits, it means that you cannot simulate exactly those circuits. So in this sense, you can say that it is a quantum supremacy experiment, but the task that they're doing doesn't have, I mean, even if the task they do is very precise, it doesn't have any practical application. So yeah, I mean, there are many things you can do with a million qubits that can be simulated but have no application. So yeah, I don't know how to comment. It's definitely a number of qubits that is larger than what a state vector simulation can do. So in that sense, it's beyond the classical methods.
Okay, so their fidelity is low, so that's why they don't have any practical application.
Yeah, with the fidelity that they have, they cannot really tackle an application where you need precision. So they do random circuit sampling, which is a different type of mathematical application for benchmarking quantum computers. But
Okay.
yeah, it's this point here, RQC. And this is one instance of RQC.
I have a follow-up question. So if we want to have a practical application, what do we need? How many qubits and what's the fidelity?
Well, if we want to have it, then it should be in this region here. So you would need more than 40 qubits, and you would need a fidelity that, I mean, an error that's smaller than 0.1%. So your 2 qubit gate fidelity should be at least 99.9%.
Okay, all right, thank you.
Any other question? How about the Zoom audience? Don't be shy. Okay, Naba-san.
Okay, can you hear me? Fine?
Yeah.
Yes.
Okay, I have an extremely naive question. Around the beginning of your talk, you mentioned that the four matrices that span the 1 qubit gate, right?
Yeah.
Is there any specific reason for this? In physics, for example, Pauli matrices are sort of standard way to span 2x2 matrices, right? It's just because of its usefulness of their properties. But here it looks kind of arbitrary, except that they are symmetric.
This is the Pauli X. This is one of the Pauli matrices.
Yeah. But that's the only one, right? The other ones are
I'm just showing some examples. There are many more.
So this is just one example, one set of the
Yes.
things that you
Sorry,
might
yeah.
use. But is there any like if you pick one like set of matrices over another,
Yeah.
is there any like reason to pick for computational purpose, or
Yes.
what is
So
the
if you want universal computation, so if you want to be able to represent any arbitrary operation,
Mhm.
then you need to select a specific set of 1 qubit gates and 2 qubit gates.
so
This
it
is
depends.
similar.
I
This is
see.
similar to classical logical circuits.
I see. So it depends on the system, or it depends on the specific system or the problem you're tackling.
Yeah, I mean, there are a few sets, and depending on, for example, some gates are easier to implement practically than others. So you have to make a choice.
I see. Okay, thank you.
You're welcome.
Okay. Any further question? Actually, I have a question for you. So Enrico, you are with the this continuum. So could you rather could you explain the architecture of the machine they are using, and what role do you play in constructing those machines?
Yeah. So I do not work on the machine. So these are some of the points here are from Quantinuum. There are actually only 2 systems at Quantinuum, 2 actual hardware machines. There are 2 of them that are called H1 and have 20 qubits, and there's one of them that is called H2 and has 32 qubits. So in total, when you submit jobs to these machines, you can choose 20 qubits or 32 qubits, but they're very similar in terms of the fidelities and the type of operations that you can run. So if you have to choose one specific hardware platform, you choose it depending on how many qubits you need. If it's 20, if it's below 20, you can choose the H1 machines, and if it's above 20, you can choose the H2 machine. And they're ion trap quantum computers, and they are based on, H1 is based on a linear trap, and H2 is based on a trap that is has the shape of a squeezed donut, like they call it a race track because it looks like a track for racing bikes or cars, where there are 2 parallel linear zones where the qubits are stored, and then there are curved connecting areas of the trap that make it easier for the ion to move from one side to the other. Yeah, I mean, I think there are more details. All the details are online. All the data for the benchmarking is also online. We published everything on GitHub, and of course, we don't publish the proprietary hardware descriptions, but everything else that is needed to run on our machine is open source.
And what do you do with this continuum?
So my goal is to find useful algorithms with practical applications that can run in this green area up here.
Okay, thank you very much. Sounds very interesting and also challenging. Okay, if there is no further questions,